David, I will ask you to make a short introduction because you are here. You are.
Oh,
okay.
I wasn't expecting to be doing an introduction.
That you are you are doing a lot of work, a lot of momentum this sector. So we are happy to have you here.
Yeah, let me just introduce you then, because I'm to say that Matteo and I started interacting a few years ago, and you visited Australia.
Yeah.
And then we had the idea of starting these parallel sessions at the Marcel Grossman conferences, and this is the second session that we had one in MG15, which was in Rome, which was very successful in spite of very hot weather in the lecture theatre. But now this is the second, and it's I think we'll be able to see that there's been a lot of progress. So over to you, Matteo, to introduce.
Okay, thank you.
Herman.
Thank you, David, for being here. And I would like to thank you all for being here, participating in this session. And also I would like to thank the organizer of this conference. That is one of the most important conferences on general relativity and relativistic physics. So we are very excited to be here and speak to this very important audience. And we have here David Blair, that is doing a lot of work in these topics of explaining Einsteinian physics, doing a lot of momentum in this interesting subject. And so we, as David told us before, this is the second session during the Marcel Grossman meeting, and we hope that this will be just the second of a long series of session during this conference, and we hope that this will be a good start for making connection between us. It is, of course, we are not together, we are virtually together, but we can meet each other and discuss on these exciting topics. So I will ask David to say something about this conference, and then we'll start with the first speaker, that is Friedrich Hermann.
Oh, sorry. So you want me to say some more?
No. I would thank David for his introduction. And then the first speaker is Friedrich Hermann. So Friedrich, you are already sharing your screen, so you can start whenever you want. We have 20 minutes for your presentation, and I will tell you when you have 2 minutes left. If you have more time to discuss, we can see later. So welcome, Friedrich, and you can start for your presentation.
And Friedrich, you need to unmute.
You should activate your microphone.
Afraid we have a problem.
No, I think
so. Do you sound is okay? You hear me?
Yeah, perfectly.
Yeah, fine. So, and you see me and you hear me. Okay, thank you very much, Matteo Luca, for the invitation, and David also. I'm happy to be, no, not in my office. I would like to be in Rome, but okay. You see the title of my talk. It's about teaching relativity. Relativity is more than 100 years old, you know, but still has not found its place in school. Just compare. Electromagnetism, which is certainly not simpler than relativity, would still not be included in the curricula 100 years after its creation. Well, there are several reasons for the deficiency. Here, I want to discuss only one of them. Relativity is still taught today, if it is taught at all, as it has originated historically. One starts with a very special relativistic effect and works through with great effort to the more important and useful general statements about relativistic dynamics. Just imagine, you want to enter a splendid palace, but you don't enter by the beautiful main entrance, but by some shabby servant's entrance. So I will describe some basic ideas of a physics course on special relativity. The concept has been tested and is used in numerous secondary schools. It is part of the cultural physics course, which can be downloaded here in various languages, among them a bilingual English-Chinese version. I cannot describe the details of our course. I merely represent some selected, a small selection of ideas that underlie its development. Here's my program. I do not explain the details of the program now. I only show it so you can see the progress of my talk. So let us begin. The laws of special relativity are obtained from those of classical mechanics by adding one extra postulate. As you know, traditionally, the choice is made for the invariance of the speed of light, invariance upon a change of the reference frame. However, this choice as a starting point is only one of several possibilities. And once you get aware of this fact, you discover that there are completely new perspectives for the development of a teaching concept. We have decided not to start with the invariance of the speed of light. We use another postulate, the mass-energy equivalence. With this choice, we arrive more quickly at that part of relativity that we consider the most important one, namely relativistic dynamics. The traditional choice, that is the invariance of the speed of light, has a rather incidental course. When special relativity came into being, light was the only known system that behaved relativistically. Einstein's famous publication of 1905 begins with a detailed and, one can say, somewhat tiring discussion of relativistic kinematics. I suppose you know it. One might imagine what had happened if the first relativistic observation had been, for instance, that a cup of hot coffee is heavier than a cup of cold coffee. If this had happened, the presentation of relativity in our textbooks would certainly be very, very different from what it is actually. Of course, mass-energy equivalence is not supported by our everyday experience, but neither is the invariance of speed of light. An advantage of the mass-energy equivalence is that we can make it easily plausible and we can discuss its consequences, even in beginners' classes. Of course, it leads to surprising and at first unbelievable statements, but it does not lead to the cognitive conflicts typical for the traditional approach. The traditional approach which questions our basic convictions about space and time. My next point. In the traditional approach to relativity, the following topics are treated before relativistic dynamics is addressed. The invariance of the speed of light, clock synchronization, the relativity of simultaneity, time dilatation, length contraction, velocity addition, Lorentz transformation, Minkowski diagram. The problem with such an approach is that one begins with the most confusing part of the theory, the relationship between space and time. It is true that students can learn a lot of physics by analyzing the same process in different reference frames. But we should not forget that we are dealing with beginners. And it's better to stick to the old rule, choose a suitable reference frame right at the beginning, Suitable means a reference frame which your problem becomes as simple as possible. Choose a suitable reference frame and don't change it anymore. And above all, don't change it in the middle of dealing with your problem. Exactly, this is usually done when discussing the twin paradox. By the way, also in classical mechanics and electromagnetism, you can create a greater confusion if you choose the reference frame improperly, or if you change it in the middle of the discussion. Well, this is why our decision was not to make reference frame changes the main topic of our lessons and to avoid them as far as possible. Above all, the impression should not be created that special relativity is essentially a theory about reference frame changes. A reference frame is no more than a mathematical artifact. Well, closely related to this question, to the frame question, is the problem of the so-called observer. The observer seems to be particularly important in two areas of physics. One is quantum physics, where the observer always appears as the one making the measurement, and the other is relativity. An observation is always made from a certain perspective. It thereby emphasizes something that does not play a particular role for the understanding of the phenomenon to be described. For example, here, I don't know if you see there are two churches. One is here, one is far away. I want to explain to somebody that the two church towers have the same height. So I say, they have the same height, and everybody understands. It is not necessary to show how I get this result by complicated measurements of the angles and by the application of trigonometry. It is true that we get all our information about the world by observing and by measuring, but the idea we form of the world in our mind is quite different from what we observe. Yet another example. I want to explain to a little child that the Earth is a sphere. So I'll show him a ball and I say, the Earth is like this. I will certainly not start with the shadow of the obelisk in Alexandria and with Eratosthenes. Now, mass energy equivalence. Let us first look at the wording. Mass energy equivalence. It is a pity that a simple fact is expressed so unclearly. The word equivalent is certainly not erroneous, but why not say directly mass and energy are the same physical quantity? Suppose you know about the mass energy equivalence, but you never have seen it expressed in the form of this equation. I now ask you to formulate the corresponding relation. I'm sure you would not write it in this way. What you would write is something like this, where K is a universal constant. But what is wrong with this equation? Every student learns in mathematics that the linear relationship between the variables X and Y is written in this way. That is, on the right side, first the factor of proportionality A, and second, the independent variable X. Now, the unbiased student might read the famous equation in this way, the following way. You would say the energy is proportional to the square of the speed of light, which is not true, because the speed of light is not a variable. And how will he read this equation? First, you will say the energy is proportional to the mass. However, since the factor of proportionality is a universal constant, you will conclude that energy and mass are the same physical quantity measured in different units. The factor K tells us how the units joule and kilogram can be converted into each other. Well, now I come to the main subject, relativistic dynamics in the Karlsruhe physics course. In our course, we introduce, it's a general remark, we introduce the extensive quantities as basic quantities. Extensive quantity means energy, momentum, electric charge, entropy, amount of substance, angular momentum, and so on. These quantities have a great advantage for teaching. One can handle each of them like a substance, like a fluid, like a stuff. One can speak about them as if one were speaking about water or about air. That is why we like to call them substance-like quantities. Moreover, some of them allow for a very direct and vivid interpretation. For instance, momentum is a measure of the amount of motion that contained in a body. That is what one would colloquially call impetus or drive. Entropy measures almost perfectly what would colloquially be called the amount of heat. Therefore, in the context of relativity, for us, it is natural to ask in the first place for the dependence of different quantities on momentum. Momentum is our independent variable. We give momentum to a body or to a particle and ask, how does it react? How does its mass or its energy behave? What happens to its velocity? In other words, we ask, for instance, for these two functions. E as a function, energy as a function of momentum and velocity as a function of momentum. Let us begin with energy. We want to derive this equation. To derive it, we take over as much as possible from non-relativistic physics. In addition, we only require the identity of mass and energy. So we start with this classical relationship, the change of the energy that results from a change of the momentum. Next, we use this equation that you know, we get this. Next, we use the mass energy identity, we get this. Next, we integrate, we get this. The integration constant we call E0 squared. So we get this square root, and here's our result. Well, maybe you didn't follow. It was much too quick to follow. That was my intention. That doesn't matter. Important thing I wanted to show is only you need only these 5 lines of math, of mathematics. And this is mathematics which is known at school. Well, we now ask what this function looks like. And well, it looks like this. The graph will be discussed in the lessons. For small momentum values, our equation changes to this. We recognize the classical kinetic energy increased by the rest energy. And well, if this is a graph of a body of 2 kilograms, for 3 kilograms it's like this, for 1 kilogram it's like this, and for 0 rest energy, our equation turns into a straight line. So in this case, the energy and momentum are proportional to one another, and we can write this relation in this form. Well, now our second question, how does the velocity of a body depend on its momentum? We write this, we replace mass by energy, we use the equation we've just derived, and we have our result. That's our result. Here, the graph of this function for several values of the proper mass of the rest mass. This is for 1 kilogram, this is for 0.5, this is for 2. And well, now what we see is that the velocity of a body approaches a terminal value as the momentum increases. And this value is independent of the rest mass. We have this limiting value. Well, up to now, K plays the role of a conversion factor. But we now see that it has simple physical meaning. Its value is the square of the terminal velocity, terminal speed. And since K is a universal constant, also the terminal speed is a universal constant, and we give it a symbol of its own. Let me see. Our diagram shows that the smaller the proper mass, the faster it approaches the terminal speed. But what is the value of k? And that's the value of the terminal speed. So far, nothing has been said about it. The answer to this question can only be obtained by measurement. There are several ways to do that. Either one increases the momentum of a particle until its velocity no longer changes in a particle accelerator, and then measures its velocity, or one measures the velocity of photons, that is particles of proper mass 0. Photons always move with the terminal speed. The constant c is usually called the speed of the light, but our derivation shows that light does not play a particular role in relativity, as often is suggested. Well, that's why we prefer to call it terminal speed. So I have to come to the end. The development of a teaching concept for the school is a balancing act. On one hand, teaching at school differs fundamentally from popular science presentations. Popular science can limit itself to showcasing the spectacular, the impressive of the scientific results. School teaching has to meet other requirements. Their statements must be logically coherent. They have to fit into the previous teaching and form a solid foundation for the future teaching, for example, at university. On the other hand, we must make sure that we do not treat high school students like university students, that we do not overburden them. Therefore, once more, two of our recommendations condensed into sentences: take the mass energy identity as the relativistic postulate and avoid reference changes. Thank you.
Thank you, Frederick. You are perfectly on time, so we have a lot of time for a couple of questions.
Thanks for the great talk. I just wanted to say that we are using some of your ideas in our Year 8 program that we are developing as part of our Einstein First project. But perhaps I could just ask one other thing, which is the description that you use about the identity of mass and energy. Well, from a sort of practical observational point of view, there is a big difference between a mass, I mean, something that's got lots of rest mass and maybe not very much kinetic energy, and something that's got lots of kinetic energy and not much rest mass. So to say that mass is energy seems to me to be a confusing way of stating it. The way I usually say it is that energy has mass.
Yeah,
which you illustrated very beautifully with your little cups of coffee.
Yeah. I would not say, first, there are many things to say, and my talk would be longer. No, I would have spoken about it if I had more time. So in my written text, it's exactly your question is addressed. Let me just make one comment. I would never say that energy has mass or mass has energy. Mass and energy are mathematical concepts. They are physical quantities. A mass cannot have energy. So that's one point. Then the other point is that the word
No,
mass,
I didn't say that. I said energy has mass.
I heard it. I believed I've heard it. Maybe. So, okay, thank you.
Yeah.
The other point is that the word mass is in the physics community also used in another sense, namely by the particle physicists. They use the word only for the rest mass. And that's understandable because they use it as a characteristic of a certain type of particle. However, this creates, if you take this for the usual current teaching, you have very bad consequences. For instance, you have a system of molecules. Now, what is the rest mass of this gas? Is it the sum of the rest masses of the particles, or is it the total energy?
Exactly.
So these are simply problems that the particle physics don't have. So we do not adopt this usage of the word. But there's more to say about it. You found an interesting point, which I couldn't address.
Yeah, and I'd like to just say one other thing, which is, when you were talking about the cups of coffee, presumably you are aware of these beautiful experiments that have been done in the last 10 years, where people have measured the change in mass of a single atom when a single photon leaves the atom.
Oh, I don't know it, but
these have been done with penning traps. They've been published in Nature.
Yeah. And of course, there are other good examples which I used to cite. For instance, the magnetic field. Of course, it has no rest mass. It has no mass for the particle people. But take a neutron star and take a liter of magnetic field, and it weighs a kilogram inertial and gravitational mass.
Yeah.
So this is impressive.
Yes, but that is sort of theoretical, but these are real simple experiments with a single atom vibrating in a trap, and they measure the resonant frequency and use that to measure its mass and the mass change when a photon leaves. Really exactly the experiment that we need to support your fundamental postulate.
There's no doubt about this. No, already Einstein knew it, and he said it clearly. So I'm a little, I think it's a pity that particle physics use the same word for something different.
Yeah.
Okay.
Okay. Thank you, Frederick. I think it's very important what you're saying about using correct words for referring. Yeah.
Sorry. I have to stop my.
Okay, so let's go to our second speaker, that is Michael Polik. Michael, if you want to start your connection.
Yes.
Okay.
I think you see it.
Yeah, perfect.
Yeah, you see and we hear.
So I can start immediately. First, thank you, Matteo, Luca, and David, for inviting us to participate in the Marshall-Grossman meeting. And thank you for the nice introducing here. And hello to everybody in this meeting. I have little time, therefore, I would like to start right away with my topic. As teachers, we were interested in the question like, is it possible to teach young students relativity without just telling entertainment stories? Or what are the contents of relativity that we count as general education? In this talk, I would like to show how we can easily and quickly get to an important result of special relativity using a suitable software. I call such software computer-aided modeling. There are many of them on the market. I currently use Coach 7, and this is the software I will present in my talk. The others work pretty much the same. The paradigms of my teaching of relativity have been and continue to be, remember what Fred said, avoid change of reference frame. Changing reference frames make physics needlessly difficult, and this is true for all parts of physics, not only for relativity. Secondly, as much as possible, avoid the use of complicated mathematics. I'm convinced that mathematical derivation do not automatically increase physical understanding. In school, the principle should be first physical understanding, then mathematics. In my classes at school, but also at university, I use Coach 7 software to create physical models. Doing this, students learn to formulate physical relationships correctly. In the background, the related mathematics will be done by the software. The company that sells Coach 7 makes the promise that, I quote, "The coach modeling activities enable you to use ready-to-go models or to create models of dynamic changing systems. Modeling allows solving realistic problems that are difficult to solve analytically at the school level. It encourages students to think, to discuss their ideas, and to clarify their understandings. To verify the model, its data can be compared with experimental data. Many years of practice have shown me that these promises are kept." In 4 steps, we want to get from a classical model to a relativistic model. The model should describe the following situation. A body should always get the same amount of momentum per unit time. We use, therefore, constant momentum current pointing into a body, and we want to see what happens. Once again, the advantage of our software is that we model many relationships graphically here without using complicated mathematics. Step 1. Here you can see our first version of our model. The momentum of the body is represented by a box. And this box looks like a container. We want the body to be at rest at the beginning of our simulation. So its momentum has the value 0 Newton seconds, or as we like to say, 0 Huygens. A constant momentum current points into the body, represented by a thick arrow. In our case, the momentum current is 1 Newton or 1 Huygens per second. Where this momentum comes from is not important here. By the way, instead of saying momentum flows into the body, we can also say a force is exerted on the body, but the thick arrow makes the momentum current much more clear. The thick arrow is a better picture for momentum current than for force. You can see the dark blue box at the bottom, and there is a letter T written in it. The letter T stands for teacher. Here I'm going to write in information that you know as teacher, of course. They are just to remind you what theory is behind the model, but they do not play any role in the classroom. So what we are modeling graphically in the first step is nothing more than the differential form dp equals f dt. To create a model, our model, we don't need to know that. The graphical model only says there is a body and its momentum increases as momentum flows into it. It's very descriptive. It's like water in a bucket. It increases while water is flowing into it. The second step, we want to know how the velocity of the body changes as its momentum increases. For this purpose, we extend our model with a variable quantity v and a constant m. They are represented here by circles. The red connection arrow from p to v and from m to v, respectively, tell us that at each moment of the simulation, you'll see later, we calculate v from the instantaneous values of the momentum and the value of the mass. To do this, we enter the expression p divided by m for v. Of course, my students know this relation from previous lessons. We start the simulation. From a selected start time to a selected stop time, the value of all physical quantities occurring in the model are continuously calculated. Together with the simulation run, we can display different diagrams in an output window. We can see how the velocity of the body changes with its momentum. In the diagram, 2 runs are shown. The first one, the mass of 1 kilogram, and the second one, the mass of 2 kilograms. The diagram shows what we have expected and what the experiment also confirms. A lighter body is faster than a heavier one if the latter has accumulated the same amount of momentum. So far, this model only provides what is already known. It doesn't provide any new insights, but, and this is very important, since the students know these results, they gain confidence into the software. Now let's go back to our model. The third step, we'll make a small change. What kind of change? Now, the students already know that when the momentum of a body increases, so does its kinetic energy. Along with momentum, energy flows into the body and is accumulated there. So we create another box, which stands for the kinetic energy of the body. We set 0 joules as the initial value of energy, because at the beginning, when the body is at rest, its kinetic energy is 0. The energy flow into the body is represented by another thick arrow here, which in this case points into the energy box. And what does this energy flow depend on? Well, there's another relation that my students have already learned in my class. The energy current depends on the velocity of the body and the momentum current into the body. So red connecting arrows show from F and V to P. P is the energy current, which is often called power. P can be calculated as P equals velocity times momentum current, or shortly, V times F. In the T window, you see, tells the teacher what the theory is behind the model. An output window shows how energy depends on the momentum. Again, this graph confirms what we already know from theory. E equals P squared divided by 2m. So far, I have only shown how I use the coach software in my classical mechanics classes. Based on the model shown, one could now create other models like falling with friction, oscillations, and much more. Only from now on, we start dealing with relativity. The only new thing is mass and energy are 2 names for one and the same physical quantity, as Fred had told. We call it energy when we express its value in joule, and we call it mass when we express its value in kilogram. Every beginner would write the equality of energy and mass like this. The factor K can be understood like this. Energy is measured in joules, mass in kilograms, so we need a conversion factor. More about this later. Frederick had told us quite a bit about this too. Quite about it. We will now see that with this equation alone, our classical Newtonian model becomes a relativistic model. You remember, this was the model that described momentum and energy in the classical case. Now, what is different in our model if we equate mass and energy? Now, this is step 4. We no longer need a symbol for mass. The red connecting arrow now points from E to V. But since energy is measured in joules, not kilograms, we need to add a factor that tells us sorry, how to convert Sorry, just a moment. Tells us how to convert the unit joule to kilogram. We call it K. And there's something else we need to change. We need to choose a starting value of energy E different from 0. Why different from 0? Now the energy E is no longer the kinetic energy, but the total energy of the body. The starting value of the energy is nothing but the rest energy of the body. In our model, we choose, for example, 10 joules. As a conversion factor for the units, we will first choose K equal to 16 joules per kilogram. You may say that is not the correct value, but please wait a moment. We will answer this question later. So far, we had calculated the velocity with P divided by M. Sorry, it was late. And we have also to adjust this equation. In this equation, we replace E divided by K. I emphasize again, we have done nothing more than equate energy and mass. And now we want to know what new facts the new model provides us with. We see in the diagram the dependence of velocity and momentum for two different rest masses or rest energies. We see, for example, for small momentum values, the velocity increases linearly with momentum. We know that from Newtonian physics. With increasing momentum, however, something new happens. For large amounts of momentum, the velocity approaches a terminal velocity. This terminal velocity is independent of the rest energy we see. These facts are produced by the model, no matter what value we have chosen for K. What a change in the value of K causes is shown in the next slide. But first, here the T window shows relation that for the dependence of velocity from momentum and can be calculated, but not in the class. We now want to investigate the question of what significance the choice of K value has. We will run a simulation 3 times, each time for a different value of K. We choose 25 joule per kilogram, 16 joules per kilogram, and 9 joule per kilogram, one after the other. What we see is that the terminal velocity also changes. It is 5 meters per second if K is 25. It's 4 meters per second if K is 16, and it's 3 meters per second if K is 9 joules per second. So we see the terminal velocity is just the square root of K without calculation. This is an interesting fact because K was something like a neutral or universal constant. So it's quite square root. That is, the terminal velocity is also a natural constant. And if we want to talk about reference frames now and only now, this terminal velocity must be independent of the reference frame. Now, one question remains: what is the correct value of K? And the answer is nature must tell us. This means we can find out the value by experiments. By experiments as they are done in CERN. K is defined as 9 times 10 to the power of 16 joule per kilogram, and thus the terminal velocity is 3 times 10 to the power of 8 meters per second. You can display many more different diagrams with our model. I would like to show only one more. Again, it shows the dependence of energy on momentum. We see the results of 2 runs with different rest energies. For small momentum values, we get the well-known classical quadratic dependence here. And the curves are shifted by the rest energy. And for large amount of momentum, the energy asymptotically approaches the dashed line. This dashed line represents the energy momentum relation for particles with rest mass 0. Its slope is just the terminal velocity. And since light has the rest mass or rest energy 0, the speed of light is just our terminal velocity. Since the square root of k is just the value of the speed of light, c, we can also write E is m times c squared in place of k times m. In the T window, you see this famous formula. Frederick had talked about this formula, which is behind the graphics. It should be emphasized again. This formula is nowhere put into the model. They result from the model, or more precisely, the model provides a graphical representation of this equation. And this figure, or similar ones, can be found in many books on relativity. You see the relativistic relation of energy and momentum. This is the red line here. We see the Newtonian approximation as a gray curve here. And finally, the asymptote. It is shown as a dashed line here. On all curves here approximate to it, this dashed line. And it describes the energy momentum relation exactly for bodies whose rest energy or rest mass is 0. I just said it. Well, my speaking time is up, I think. I hope I could show you using a computer-aided modeling system we can get from Newtonian mechanics to relativity in just a few steps, and only require mathematics knowledge that every student already knows anyway. I have tested this in the middle school several times with success, and it remains to say thank you for your attention.
Thank you, Mika. Again, we are perfect on time, so we have time for a short discussion for a couple of questions. So are there any questions? I have one question for both of you. I totally agree about the emphasis on the role of frames, but you know, usually it's difficult to explain the importance of choosing the correct frame, and within the frame, the correct coordinates for describing a physical problem. So according to your experience, how can you teach to a student how to choose the correct frame? Which is the correct frame for studying?
I think I have not to discuss what is the perfect frame. This is a question I think the students are not very interested in. Here we live in a classroom and we have a body, and we want to accelerate this body. That means we will give him a special amount of momentum and it will move. That's all. So you see the first model I've shown, it's just describing this situation. It's very easy to do this. And I do this very early in my class when we don't have the aim to discuss relativity. It's normal classical mechanics. Also the situation with kinetic energy. In normal classes, you talk about both without pointing out any special frame. It's a classroom. So it's the same. Okay, I think Frederick wants to say something.
May I comment something about in the cultural physics course? We don't address the question of reference frame. We always take the one who is appropriate at the beginning. Yeah. However, there is in the class in the 11, I don't know, it's higher secondary school. We have one teaching unit of about 4 lessons of class, which is only about reference frames. But then we don't limit to mechanics. We only, the teaching objective is not to solve problems in different frames, but to understand the role of reference frames. Yeah. For instance, we also take things in the same teaching unit. We address the question of an electron beam. You know, it has a magnetic field, and then we move with the beam, and the field the magnetic field disappears. And so we give many examples about the consequences of reference frame changes, and also the falling apple and the falling person and so on.
Yeah.
All together, but the message is not to solve particular problems. Only say, you know what physics is like. If you apply mathematics, these things happen.
Okay, thank you. Yes. Thank you for your answers. So if there are no more questions, we can go to David.
Sorry,
yeah, of course.
If I could just ask one. So you said that what you presented, you've taught at middle school. Yes. What age students?
What age? About I think 14 years old.
And
the first models I used in my class earlier. I used this this coach software not only for teaching relativity. I use it in all of my physics courses, in mechanics, in thermodynamics, or in electrodynamics, from the very early lessons to the late lessons. In the high school, I discuss, for example, charging a capacitor and so forth. This is a software, so the students are familiar with this software right at the moment when I start with them teaching or telling them about relativity.
So I just want to clarify, because in Australia, students of this age wouldn't have, I would not expect to be able to teach class. Are these at that level? Are these students streamed? Are they selected, you know, for a scientific, you know, for a scientific stream, or is it the average general students?
Normal students, no special students. I can tell you why. In a school, I found a book was written. It's a very old book, was written for 12 years old students. And in the book, you find things about relativity and so forth. And if a student in this age comes to me and asks me about relativity, I cannot say to him, you have to wait until you are 17 years old and I will give you the answers, because it's a very, very long time and they don't have like to wait. So I have to give them answers at the in this moment when they have the question. And so I think I have to give answers about relativity in the moment when they ask.
So then can I clarify one more thing?
Yes.
Sorry, then do they see any of that mathematics?
No.
That you showed us?
No. They don't see anything of these equations, but as I say, the graphs, the diagrams, they discuss the diagrams, and I give them the values, for example, the value of C. And I tell them they have measured in some this value. But when they are older in higher level school, then I will show them how to find these equations like Fred had just told.
Yeah, okay.
But it's in higher school. Yeah. But they discuss the problems of speed of light, etc. very, very early. Even it's not written in the curriculum, because I think every school boy, school girl should know something about relativity. That's my opinion.
I completely agree with you.
We-
Yeah.
Yeah, me too. We totally agree.
Mhm.
Okay. Okay, Michael, thank you again for your talk. So
It was a pleasure.
next speaker, Matthias, you can.
Hello.
Hello, Matthias. Okay. Okay, you can start with your presentation. Thank you.
Okay, so you can see it? Yes.
Yeah.
Okay, thanks a lot first, the organizers, for letting me speak here. I don't know if it's really the right session or the thing, but I just wanted to show it to somebody, and maybe one can include it for sure in public lectures, but probably also for school students, but then more at the end of the school time. Yeah. So I want to explain two really apparently absurd statements. Yeah. The first statement on the left side is that one can describe the what the matter is doing in a neutron star merger with different ballroom dances. This is the first thing I want to speak, and the other thing I want to speak is that the architecture of the German Reichstag, the parliament building of Germany, looks exactly like a black hole. Yeah. So when one uses such things, and I often use that in public lectures, most of the people like it, and they see something behind, and probably you will also see that only at the first glance it is absurd. And now we want to go in the first example. Probably you heard the planetary talk by Michael Kramer about neutron star pulsars. So pulsars are rotating neutron stars, and he was speaking a lot about the so-called double pulsar. So in our galaxy, we know several neutron stars in binary system, and the double pulsar is such a thing. So there are two neutron stars orbit around each other. Each of the neutron star has a magnetic field, and it oscillates around itself. And due to the orbiting motion, it emits gravitational waves, and as a result, they come nearer to each other, and finally will collapse. In this binary system, the double pulsar, this will happen in 85 million years. So, but we were really lucky that we saw with the gravitational wave detectors in 2017 the first neutron star merger event. So a pulsar merger event, and just to remind you, with the gravitational waves we saw here, the in spiral phase, so the last orbits of the two neutron stars moving around each other, yeah, and then they merged. Unfortunately, then the emitted gravitational wave frequency went out of the spectrum, but we saw then with a totally other detector, with a gamma ray detector, roughly 2 seconds after they merge, a kind of gamma ray. But the question is, what is going to happen here in between? And there the people are now quite sure that the following happened, that the two neutron stars merged and created a so-called hypermassive neutron star, which lived for maybe 1 second, collapsed then to a black hole, and then the material was falling into the black hole and created the gamma ray burst. So here on the left, you see the amplitude of the gravitational wave emitted during this in-spiral phase. Yeah, and here is the merger, and we did not saw this post-merger phase here, where the remnant emits gravitational wave at a much higher frequency, but with computer simulation, we can look how this looks like. And here we are now at the late in spiral phase. Here you see the density of the 2 neutron stars. And now you have to carefully look to see the dancers. Yeah. Well, I'm a hobby dancer and I will explain it to you. So this is the in-spiral phase. And now when you look here at the density structure, then there is a kind of double core structure first. This is the so-called violent post-merger part. We are now here. But then after some time, the density in the interior is the highest, and it rotates very strongly. Gets in the interior more dense, and then it collapses here to a black hole. Just wait until, so it gets here denser and denser, and then collapses to a black hole. And there the ring down phase of the gravitational wave comes, and a black hole is created then here. Okay, I will explain you now, or to show you that the different phases of such a neutron star merger looks like the in-spiral phase, looks like a Vienna waltz. Then we saw this double core structure where we had a so-called disco fox phase, this wild transient phase. And then when the density is the highest in the center, it's a kind of merengue. And at the end, I will explain that the collapse to a black hole is like a tango phase, where at the end of a tango, of an Argentinian tango, the people feel when the music stops and they freeze in. Yeah, but we will come to that. But here's maybe not so important. This disco fox phase has in the spectrocom a lot of different frequencies in the gravitational wave, but the merengue phase here has only one frequency. We probably will see that with the next generation gravitational wave telescopes. Now the neutron star merger then come the in-spiral phase. So the 2 neutron stars move around the magnetic field. Now they merge, and this wild disco fox phase comes, where the double core structure is. But then they are nearer to each other, rotates, and it's a kind of merengue. The density and temperature also gets higher, and yeah, in this case, it should not happen in all of the cases, but in this case, it's collapsing to a black hole, and there's the tango phase. I will speak about the tango phase then. Okay, so to speak about the tango phase is we have to understand what black holes are. And one often used example of curvature of space-time is that space-time is like a shade, and when you put energy in, it curves and it looks like that. So here you have the compactness of this object which sits here and curves the space-time. This is not a black hole, it's kind of curvature of the Earth or something like that. But then you make the object more compact, and then it curves more. Then comes a kind of stability limit. It's exactly at this compactness range over there. There you can show mathematically that no stable objects can exist anymore. Matter have to collapse to a black hole. And so we got this black hole. We created this black hole now, and these so-called embedding diagrams are often used to illustrate the curved space-time. These are the space-time funnel of a black hole. Okay. Maybe I have to go back to this. Here you see particles moving around. This is the ISCO, the last stable orbit about the black hole. But here at 3M, there's a so-called photon sphere where light is moving around the black hole. We will come to this later. But these embedding diagrams are informative. But to really see the structure of a black hole, one has to use these space-time diagrams. Here's, for example, such a light cone in a non-curved space. This looks like that. There is a future, the past, but particles have to follow inside here. They can't travel over light over here. If you looked at for a black hole, the space-time looks like that, and when you come nearer to this event horizon here, the space-time funnels come like that, and this is the viewpoint from an outside observer, which means when you let from the outside something falling in, it has to follow here. But as the light cones become smaller and smaller, for an outside observer, it looks like that the thing what you throw into the black hole becomes frozen at the event horizon. It stops there for sure. The light get also infinitely redshifted. So after some time, you can't see the object anymore. But for an outside observer, when it let an apple fall in, the apple is becoming, before the event horizon, it becomes slower and slower and then freeze in there. Yeah, this is the interior of the black hole where space and time moves in. But for sure, when you go into the apple itself and you fall with the apple into the black hole, it overshoots this barrier here. But after the event horizon, it can't give information to the outside. These are the space-time diagrams and so-called advanced Eddington-Finkelstein diagrams. But now coming to why the German parliament looks like a black hole. So at first, so this is the German parliament building. They have built it in such a new thing over there. When you look carefully here into that, there is this thing over there with mirrors, and this is here in the inside of the parliament building, and it goes like this, and it looks exactly, when you look into that, it looks like such a space-time funnel where the real singularity sits here. So this embedding diagram. But more funnily, when you go now to the inside, as an outside observer, you can go into the inside of this building. Here is exactly this funnel which goes there. The politicians, they talk in this thing here near to this real singularity. But the outside observer, like the people here, they can just come to a circular barrier from where they can peer down here into this debuting things over there, and at this circular barrier here, photographs of decisive events of German history are displayed over here to remind the visitor of the responsibility for all of us for the future, and they are warnings against forgetting also the old things which happened during the repression of the Nazi era. But coming back to the picture of the black hole, so these historical scenes, they are like frozen on the event horizon as reminders for ourselves. But there is another thing when you so here on the left side, I have a little movie how this looks like here. And so here are the visitors. They can go here and take a lift. One can also move up here. But when you look back at the lift, which was over there where the people then can go down, there is a picture of me taking a photo in the lift. The lift is saying approximately at 3/2 of the Schwarzschild radius, and the lift is made with mirrors. So when you look there, light is infinitely reflected like the photon sphere. Yeah. So yes, I have written an article about that. It's quite a time ago. You can maybe look into that. After I was, I have to stop soon. Just at the end, after I saw that, I went out, and next to is to the German Parliament is the Brandenburger Gate. No. First, I have to say something because of the tango phase. Yeah, the tango phase, when the hypermassive neutron star collapses to a black hole. Yeah, this was also in the Nobel Prize article by Penrose. Here you have the matter, so the neutron star collapsing to a black hole. Then the event horizon is here formed, but an outside observer can only see this frozen picture of the tango phase. Yeah, and this is why the end was a tango phase. I have to leave soon also here, because I have to give another talk about this collapsing things when a black hole is formed. And funnily, this last frozen picture of the tango phase, there the matter is heated up in the neutron star, and when you plot here the temperature versus the baryonic density, it looks like a swan, and this is the last picture of the matter what is doing. But coming to the end, so after I was at the German Parliament then and saw this, I went out to the Brandenburger Gate, and next to the Brandenburger Gate was a place which was vacant, but where now the American embassy is in. Yeah, and there artists arranged some 60 bears standing in a circle with the country names on it, and one bear with an Einstein face was a side of that, and on this Einstein bear was a citation of Einstein written: "Peace cannot be kept by force; it can only be achieved by understanding." And yeah, here I have some. Here you see, for example, this Einstein bear with this circle of bears, and with this I want to end. Thanks a lot.
Thank you, Matthias, for your talk and suggesting our different place to take our inspiration to teacher relativity and relativistic physics, from dance to architecture. So very interesting. So we have time for a question.
I'd like to just make a comment, which is that we, as part of our Einstein first program here, we taught very young children about neutron star coalescence, and we used a play in which they acted the sequence of discoveries from Einstein to neutron stars, and then binary neutron stars, and finally the neutron star coalescence. And then the two children acted the neutron stars, and they spun around a little bit like your dancers.
Oh, really?
And,
Okay.
this thing was performed as an opening event by only 8-year-old children.
Okay, so if 8-year-old children can do that, then probably older can, yeah. So maybe it's a way to just the people learn something, but it is not as hard as only seeing equation, and so yeah.
Exactly. Mm-hmm.
Thank you again, Matthias.
Mm.
So the next speaker is Sven Weissenborn.
Okay, I will share my presentation.
Yeah.
So I hope you can see it.
Yes, perfect.
Perfect. I'm a PhD student from Ute Kraus from Hildesheim in Germany. And I want to talk about the teaching of exploring the curved spacetime near neutron star with virtual sector models. So first of all, I want to say that GR is not part of the most of the curricula in the German states. So just in 4 states, GR is a main part of the curriculum, but in the most of them it isn't. So you have the possibility to teach it, but it's not very common presented in our curriculum. So to force this grievance, Ute Kraus and Corvin Zahn developed an approach to use the geometric character from GR and teaching just with geometric concepts the idea of GR. So I want to introduce the sector model, maybe you know it. And first of all, we are going from a curved surface, like a sphere, and divide the curved surface into pieces and measure the length of these pieces. So we have several curved pieces, and we will construct plane pieces of this surface. So we build some sectors. With these sectors, we can describe the geometry of our curved surface, and we can construct some of very important things like geodesics and so on. When we glue these sectors together, we can see that the sector model is very good. It's a very good approximation of our curved surface from the sphere. So one important thing in GR is the construction or the developing of geodesics, because geodesics are describing the path of light and particles in space-time. And you can construct geodesics on sector models just with pen and ruler. You don't need the different mathematics, and you don't need the higher mathematics to solve different equations, but you can just draw these geodesics with pen and ruler. So geodesics on a sphere like that are starting parallel, and we can see that they will merge at the North Pole. We can do the same on our sector model. In one of our sectors, I hope you can see my mouse cursor, the geodesic is a straight line. When the geodesic is crossing the border of a sector, we need another one, the neighbor of this one. And then the geodesic is going over the border in the same direction. And with our sector model, we can show that the same geometric phenomena, that two parallel starting geodesics will merge at the pole, can be done with our sector model too. These sector models are typically made from paper. different sector models are shown in different articles from Ute Kraus and Corvin Zahn. And we wanted to combine the idea of the sector model, typically shown from paper, with a computer model. So we developed an application which is called VSEMO, stands for Virtual Sector Model. It is web-based and it's interactive. I just want to show you the simulation. So here in this part of VSEMO, we can see the same sector model, but with another texture. So with Europe, we have the possibility to zoom in and to zoom out, and we can construct these geodesics I have shown you in the picture before in an interactive simulation. So we can put the sectors together, we can move them, we can rotate them, and we can draw our geodesic over the sectors. VSEMO has some features that will help students to work with our model. So first of all, I want to show you that VSEMO can tells us when we are doing something wrong, like drawing a geodesic over the background. So between the sectors, there is nothing. This is not presenting the curved surface. So VSEMO will stop our geodesic at a border where no snapped partner, no snapped sector is. So we have to put them together and then we can draw our geodesic over the sectors. So we have the same image made from cardboard sectors in a virtual way. So in another experiment, I want to show you another virtual sector model. For that, we have to go on a thought experiment, and we will go with our friend, the astronaut Carl, to a neutron star. So we want to build a neutron star sector model from the inside and of the outside of the neutron star. First of all, we begin like before on our sphere. We have to subdivide the room of the inside and of the outside of the neutron star. We build a grid, measure the length of the grid of the outside and from the inside. So we have to drill some holes through the star and then send these lengths to the Earth. On Earth, they built a sector model from our measured length. And I will show you this sector model in an interactive simulation too. So this is our sector model I have shown you. And we want to go on a vacation with Carl and his girlfriend Lisa. And they arrived in this sector. In VSEMO, we have the possibility to make small lectures in a ongoing path. So students have to go on our slides and learn something about our sector model. In the first one, we are telling that Lisa is going onto the surface. And now she wants to send Carl a light signal to tell him that her landing was successful. We see that our light signal is a straight line. So the geodesic is describing our path from our light. Now she has to send the information to Carl. In our VSEMO simulation, we can change the direction of the geodesic at the starting point. And VSEMO will complete all the path from our geodesic. So we can say, okay, our geodesic is crossing Carl in a good way, and VSEMO gives us a feedback we did it right. But we can see that our geodesic is a straight line. In the next step, Lisa is going over the neutron star and is sending her light signal to Carl continuously. But then the light signal doesn't arrive at Carl's spaceship in K4. And our task is now to find the last position where Lisa could send a light signal to Carl. We are going to do that. And we can use some different automatically functions to do that. And now we have to find Lisa's position while construct geodesics. And we found her on the surface at this point. Lisa is going on her explanatory trip and is going over. And after some time, Carl will get a signal too. And now we have to determine Lisa's position when Carl receives her signal again. So we are going on, use our geodesic in our sector model, and find the position on the star where Lisa can send the first signal again to Carl at this point. So when we look at these points, this is something special and something interesting, because we see that we can reach with light signals parts of the surface behind the half of the neutron star. Everybody of us is knowing that this is forced by the light bending, because the mass of the neutron star is so big that it curves the space-time around it. But this is a way to construct and to describe the phenomena of light bending just with geometric concept. So in our picture, we can see on the left side, thank you to Thomas Reiber for the pictures, where the neutron star is shown without the bending of light. And on the right side, we can see our neutron star shown with the phenomena of light bending. We can see behind the poles on the surface of our neutron star. Another thing is not just to subdivide the space around a neutron star. We can subdivide the space-time too. And subdividing a space-time is something that is really easy, and we know it from our daily work at conferences like the Marshall-Grossman one. So we can subdivide a space-time in space and time direction. So we have different rooms where happening different talks at different times, and we can say that at room 1, at this time sector, there are different events happening inside of the talk. And using this idea of subdividing a space-time, we can do at a ray near to our neutron star, inside and outside of the neutron star. So we subdivide the time and the space of our neutron star inside and outside, and we can use this idea to calculate the sectors model like I've shown before. Normally, to do that, we use the metric from inside and outside of the neutron star and calculate with that the geometric shape for our space-time sectors. So this image shows space-time sectors in our Minkowski diagram. Each of these sectors has Minkowski geometry, and each of these sectors is a small Minkowski diagram. In all of them, I show you a small gray line. These lines describe the light cone. So we can see the speed of light in all of these small Minkowski diagrams. When we build a bigger model from our space-time of our neutron star, it is shown here. And just to explain, in one of these rows, we are just describing the space of a ray inside and outside of our neutron star, and the time is going on in this direction. But we have one problem with our sectors from space-time. So when we want to put them together, we have normally to rotate our sectors, but we can't do that because when we rotate a space-time sector, we can see that the light, the speed of light is changing. from one inertial system to another. And this is not possible, so we have to Lorentz transform them. And this is something we can do in Visemo too. I would like to show you this one. So we have our bigger model of our spacetime from our neutron star, and we have here different spacetime sectors of the outside. We have the possibility to transform each of these sectors and their shape, to put them together, and to describe a geodesic as a straight line in our model. Just with one click, we can put all of these sectors together and construct our geodesic as a straight line through our whole model. And when we put them in the original state, this just needs some time because it's a big model. Come on, computer. We can see and follow our geodesic, and we can see that a particle which was near our neutron star was free, is moving to our neutron star without the description of any force or something like that, just from the curved space-time near our neutron star. With this idea, we can describe some different phenomena shown described from the GR, like the idea of gravitational redshift. In Visemo, we have the possibility to use a small triangle to measure length. And in this model, we can see these are two light signals sent from a lander to our spaceship. We can measure the time difference at the beginning, so 3 time units. We can use the same triangle at a spaceship in the difference to our neutron star, and we see that the time difference is now 4 time units. So the signal is redshifted. You can zoom in so you can see it a little bit better. And a last one I want to show you is described when we drill some holes through our neutron star and we let a particle fall into that. We can follow our geodesic and we see that the particle is falling into the star, falling through the star, coming out of the star, and is oscillating in this hole. Just describing with a geometry concept without any mathematics. So if it was interesting, you can read the articles from Ute Kraus and Corwin Zahn. You can find these articles on our website, spacetimetravel.org. And if you like to test Visemo, you have the possibility to do that on this link. And if you have any further questions, you can send me an email. Thank you for your time. I hope you enjoyed my talk.
Thank you, Sven, for your talk, presentation. Are there any questions for Sven? Comments?
Can I ask if it would be quite easy and straightforward for anybody with any normal laptop to use these in a classroom without too much training?
Yes, we've developed Visemo and tested it in several solo interviews with students, and we just gave them tasks to do something, and they get no more instructions, just in Visemo, and they are doing it very well. So they are learning the work with the sector model from doing it with Visemo.
And what age students?
From 15 and above. So at class 9 and to class 13 and students at the university too.
I see. Yeah, thanks.
May I ask a question?
Of course.
Sorry. Yeah. Okay. I like very much this approach. For me, I had really to concentrate to follow all the details. It was very high concentration of things. And there was one point I'm not sure if I understood. Before you addressed space-time, there were geodetics only in space, no? At the beginning.
Right.
But then you told about the path of the light in a neutron star. But the light doesn't follow a geodesic in space.
Yes, that's right. But when you see, I will show you. When we see this image, it's just a spatial sector model, but it's underestimate the true path the geodesic will follow. So in the reality, the bending of our the bending of the light is bigger than shown in our model.
Okay. Then I understood. Okay, thank you.
Okay. So it's just an analogy to explain it, but it's underestimated and we are not going over it.
Okay. Thank you again, Sven, for your presentation.
Thank you too.
So next speaker is Stephen Price. Okay.
So yes, I'd like to talk about interactive visualizations. I'm from the same group as Sven Weissenborn. Yes. This is what I'm going to talk about. This is a picture taken from my simulation. We have here a virtual 3D model, photorealistic of our town. It's Hildesheim Marketplace, equipped with some additional objects. And this image is taken from my simulation program at a high-speed observer. And what you can see is bending of buildings and buildings that are in the distance are they look like very far apart, and that's optical effects. And I want to explain a little bit about that, how this simulation works. I want to go into detail in the development of the algorithms that are necessary to have such a simulation that works interactively, because this is the main part of my PhD project. And I also want to give you an impression how we implement such simulations in our school lab for the teaching of special relativity. So as we have heard, or as you know, when we want to introduce relativity, we usually start with two postulates. So if I say two, I mean the first postulate is that in every inertial frame, the physical laws look the same. And the second postulate, as was mentioned before, is constancy of the speed of light. And as you introduce these postulates, you can derive from this the relativity of time and length, and you condensate out of these the famous concepts of time dilation, which is characterized by a moving clock that runs slower, and of course the length contraction, which states that a moving body is shortened in the direction of motion. As we have heard by Friedrich Hermann and Michael Polik, that changes of reference frame together with these concepts, time dilation and length contraction, can quickly lead to apparent paradoxa, you know, twin paradox, or the ladder paradox. And this might be obstructive in teaching relativity. This is why Friedrich Hermann pointed out that we should avoid reference frame changes. But I think this might undermine the strengths of the first of the two postulates, so that we can express our physics in any reference frame. And that's why I think my simulation has some power to work in this regard. So I will show this later on. At first, I want to think about well, when we want to investigate how the students' understanding of this concept is. At first, we pose questions and tasks and evaluate these. And then the students have some tools at hand to treat relativistic problems. In a paper of Scher, this was she gave an overview of these tools. First is qualitative reasoning. So with the basic concept at hand, explain what happens. But this tool, of course, needs a high level of physical intuition to solve the problems correctly. The second, maybe the most common, is quantitative computation, where you get, in this case, a Lorentz transformation to transform coordinates from one reference frame to another. But this, of course, needs some computation skills for the students. And in this case, it also needs some intuition, because here I've also written down the formulas for time dilation and length contraction, and it is needed to think about carefully when you are allowed to use these formulas. Yeah. The third possible tool is to use a space-time diagram or Minkowski diagram. Here you can visualize motions of different objects or observers, different reference frames. But also it needs some exercise to use these diagrams correctly. Of course, in the end, all of these tools are equally valid for solving of a problem or to answer a question. But the students need to learn to use these tools and handle them with care. And well, we thought there's maybe something missing, because from our usual context in physics, we know we are doing experiments and derive physical conclusions directly from our experiments. Well, in the case of relativity, such experiments are not available, but we can use our computer as a laboratory to conduct maybe thought experiments or experiments in a different way. So we created an interactive computer simulation to do that. And as it is known from other people, if you create an immersive computer simulation, this can help a lot in student learning. Yeah, another interesting problem which arises if you talk about if you talk with people about relativity is well, what would happen if we move with relativistic speed? What would we see? How would the world look like? And this problem can be solved with our interactive simulations. So now I'm going to tell you about the basics behind these computer simulations. There is a well-known computer graphics method, which is called ray tracing. Relativity is prominent dealing with light. So here we also investigate light rays and backtrace them from the observer to the source. In this picture, you can see how this is done. So you shoot some primary rays from a camera through your image plane and want to know how you have to color your pixels. So you have to shoot it to the objects. And of course, you're not done. If you have hit the object, then you have secondary rays where you have to check for visibility. Mainly this means if one of the secondary rays can be connected with a light source or lie in the shadow. Yeah, this technique is a well-known computer graphics technique, and it's the only technique which can create photorealistic images. Here I've taken an example image from a ray tracing library, from a paper dealing with these algorithms. And here you can see a very realistic car. And this is only due to the exact or the correct physical implementation of reflections and refractions. In the standard graphical approach, which is called rasterization, these effects can only be modeled to some extent. So you can only mimic them in some way. The problem about ray tracing is, on the other hand, that is, as I said, computationally challenging. For every ray you shoot in your scene, you have to determine the exact object that is hit by the ray. So usually you deal with meshes, which consists of triangles as surfaces. So you have to check which triangle is hit by a ray. So at first sight, you have to check with every single triangle, and this would be a lot of computer work. So we have to deal with this problem. So we have to reduce the computational complexity if we want to have an interactive application. There are a lot of work in this field because people want to promote ray tracing to an interactive computer graphics standard, and they are they can do this now, and the underlying structure behind this is the so-called KD tree. The K here stands for the number of dimensions, so some dimensional tree. What you actually do is space partitioning of bounding volume hierarchies. This means you take boxes around your objects, which are simple objects, and you start with your tree, with your root of your tree is a box around your whole scene, and then you subdivide this box into two halves, and then you go into one of these halves and subdivide it further, and so on until you are in the leaves of the tree, and there you have to put your triangles in the leaves, and you do only intersections with your rays with objects in the tree, so you don't have to compute intersections with all objects in the scene, but only with the most relevant ones. It's interesting, this algorithm has a complexity of, has a logarithmic complexity. Compared to that, the standard rasterization technique has a linear complexity. But the underlying steps are a little bit more, cost a little bit more. So the question with this algorithm is where to do the splitting of your nodes, of your boxes. And to find an optimal split, you have to use a so-called cost heuristic. Therefore, you take your splitting cost and compute it as one additional traversal and add the intersection cost with the number of objects which are weighted by a probability, and you have to add the number of objects and the probabilities for the left and right sub boxes. And these costs and these probabilities are well known. For a 3D case, they come from integral geometry. They are even extendable to Riemannian geometry. And what I did, because I do ray tracing in a four-dimensional space-time, I generalized this concept to a space-time structure. So I deal with a four-dimensional tree, which partitions my whole scene. And with that, I can do interactive ray tracing of a relativistic scene. Now the question is, which kinds of scene is suitable for such application? And we thought about, well, we want to choose a familiar scene. You have seen it, the town center with some famous buildings, because if students come to a school lab, they usually know these surroundings, and this increases the immersion of the simulation. And what we practically do is reduce the light speed. So you can investigate the relativistic effects at a walking pace. This is also, this has been done in another approach for relativistic simulations in a slower speed of light, which is a MIT developed application. And but they used a rather alien landscape. Well, and people usually ask, well, why don't you do a space scene with sun and the planets? Well, this would be quite boring because you only have spherical objects which are quite far apart from another, and you fly like 20 minutes from the Earth to Saturn, and there you only see a small green point getting bigger. Yes, at this point, I wanted to show you my simulation. Can you see this now? This okay, great. Yeah, I'm now on the marketplace. I can move freely and experience what happens if I now go to some speed and look around and see how the objects distort in some way and move around. I've also implemented clocks which can be read off to compare with the own time feelings. And the best effects you get if the speed is quite high. And you can do some course around. And this is how we usually start our teaching. When we do this kind of stuff, we let the students explore our interactive visualization. Yeah, I have to do a remark here. So as you have noticed, Doppler and searchlight effects are not included in this simulation. This is because the visibility gets quite low if you enable these effects, because the color is shifted quite at quite low speeds. And searchlight effects even make things worse. So you only have very bright light coming from your front, and the rear parts gets very, very dark. And because of that, and you also are not able to have information about the whole spectrum. So yes, these are the reasons why we leave this out and leave only the geometric distortions. Yeah, now I come to the teaching strategy for this type of course when we do this in our school lab. In the introduction part, we use the concepts of relative and absolute statements or viewpoint dependence, and emphasize here that speed.
You have a couple of minutes.
Okay. And make this emphasis on the relativity of speed. We go to the postulates and say, okay, things change when we now have the postulate that the light speed is absolute. We introduce our virtual world, and then we want to explore the world. These distortions can then be explained to our students with easy visualizations. I have here one where you can see how a moving camera captures a photon from behind, so that the observer is thinking that the photon came from another direction. We know this as a relativistic aberration. And in the second part, we can let people observe some things. I want to show this to you as a video. In this video, you can see a spaceship moving through this nice building, and you can measure the time it takes, and the speed is 95% the speed of light. In my simulation, the speed of light is 1 meter per second. So you can also calculate how long it takes. In this case, it was 17 seconds. And now you can also do this by yourself. You can fly through the same route. And we want to measure again, how long does it take? And we came to the conclusion, oh, this is here, in this case, it's about 6 seconds. You do this for several different velocities and get to the point that these measurements conflict. So we have that time is a relative concept, and this exploits the possibilities of frame change. So here you are able to change it by yourself, and this is the strength of these kind of simulations. So if you have misconceptions like, oh, when I move very fast, then I can only go in slow motion, you can here directly experience that this is not the case. Okay. I have some more applications in my program, which I can very quickly show to you. This is a simulation where I put different clocks in different frames, and here you can observe how the clocks are moving. For the moving clocks, it's a bit difficult, but you can also again change your frame, watch these clocks as they are co-moving to you, and here again, you can exploit the reference frame change and can go back and forth between the two different frames, and can investigate what's with the clock speed respective to you. And I want to show another thing which incorporates fully my abilities. So here I have a simulation of wheels together with shadows. So this gives a whole lot of interesting phenomena which can be investigated visibly. And with this, I want to end.
Thank you, Stefan. Very, very beautiful talk, and the power of visualization is very useful. I have one question. What about the feedback you have from students? What is the most difficult thing they have to understand? Because it's much like a video game, but how can they distinguish what are the physical principle and which your simulation are based on. So what are, according to you, to your experience, what is the most difficult thing to convey to these for simulations?
Well, the difficult things to convey are, I think, not the simulation itself, but beforehand. You have to convey that you have to put in the absoluteness of the speed of light. And well, after you have done these measurements, you again convey with the light clock experiment. And with careful measurement, you can get exactly the square root factor. But since it is an experiment which they can do, we have a good experience. So we think with this type of game, they can learn a lot.
Okay, thank you, Stefan, again for your presentation. Are there any other questions? Just for time for one question, then we go to next speaker.
I have one question.
Yeah, of course.
You gave a few examples into games that might resemble the what is it, slowed down speed of light. Have you ever heard of the what is it called, real-time relativity?
Yes.
Yeah. Does it? I mean, it seems like it portrays a similar concept. I mean,
yes, it's basically the same concept, but they moved their scenes into space. I don't know, and they used very large objects.
Yeah.
Yes.
Yeah.
So the concept is there are some more of these type of simulations, but I think I'm the only one that has a lot of moving and accelerating objects.
Yeah, because you include,
and it's interactive.
Yeah, and the different reference frames in relation to it.
Yeah.
Is your simulation available? I remember like speaking to Corvin and Corvin Zahn, and he said that, I mean, there was one particular computer that had the power to actually play this animation.
This is why I'm working on these algorithms, so that it now I'm just using this simulation on a usual laptop, because with these concepts you can do it. We have a large cave simulation, which is a surround projection, where all the screen around you in a large room works, and therefore we need a quite large computer to do that.
Yeah. One last question, and then after I'll stop.
But it's not published yet.
It's not published. Oh, looking forward to it.
Yeah.
When Stefan talked about giving this to 15-year-old students, and I'd imagine that 15-year-old students would be kind of really interested in using this and just understanding relativity. What are some questions that you might ask that is inside, I don't know, the worksheet that students have, or questions that you ask students to discuss in groups? What is an important question that you've decided to use in relation to this simulation?
Well, usually we teach, so we give input, so they have to measure these times for different speeds, and then come to the conclusion, something cannot fit together, and then together with the teacher, they via the light clock experiment, they derive to the conclusion that something cannot fit together, and how this is related. And in the end, well, we do not test after this. So we can also do the same thing with length contraction. and investigate this phenomenon. But yet we have not done any testing of the course in the sense of educational research. I do only or mainly physics algorithm, so the development of the application.
Thank you.
Okay, thank you. So the next speaker is Gabriela Isabela Vera Garcias. Gabriela, if you want, you can. Okay, thank you.
Okay, can you see my screen?
Perfectly, thank you.
Okay. Well, good afternoon. My name is Gabriela Vera, a student of Physical Engineering at Universidad Autónoma Metropolitana UAM, Unidad Azcapotzalco in Mexico City. First and foremost, I would like to thank the organizing committee for allowing me to present this discussion, which is part of the final work for my degree in physical engineering. And congratulations to all the participants, because the presentations are really good and complement a lot the future discussion of this work. I have the pleasure to present this work with Dr. Cesar Simón López Monsalvo, Cátedra CONACYT, Commissionate at UAM Azcapotzalco. So let's begin. General relativity is slightly over a century old. It is clearly recognized as one of the outstanding achievements of human intellectual endeavors. It has certainly reached the popular culture, and it is more likely than not that a high school student has heard of it in some shape or form. Yet its formal basis is not revealed to most people. It lies somewhere in the second half of a standard degree in physics, and most physicists won't ever use it directly. The reason for this appears to be the sophisticated mathematical tools of differential geometry, Riemannian manifolds, tensor analysis, nonlinear partial differential equations, and so on. Indeed, general relativity is challenging from the mathematical perspective, but it is even more so in its foundational principles, but for different reasons, since one has to deconstruct years of learning and intuition. It forces us to rethink what a force is, to rebuild our empirical notions from a different perspective, and to reevaluate our general understanding of motion. We believe that the sooner these ideas are present, a closer insight of physical reasoning could be conjectured to the younger syllabus. Our work explores a way of introducing the essential physical ideas from a critical perspective. That is not only presenting the empirical postulates, but asking ourselves what is the cost of our own assumptions building them. To that end, we will explore the dichotomy of explaining gravity either as a force or something else. Our work presents the student with a decision to be made regarding the understanding of a clear-cut phenomenon, namely gravity, as the force in Newton's universal law of gravitation, or as non-inertial effect preventing us from following our inertial path. How much math do we need to do that? Let us see. First, we will see what we get from inertial motion. Do we really understand it? Okay, let us see. First, inertial motion, we are told is easy. Just go straight at the uniform speed, and that's all about it. This is the way Galileo roughly defined it. But to him, was no ambiguity of what a straight line was on. To most people, there is no ambiguity either. This is the point of our argument. Let us ask ourselves to define with words what a straight line is. Surely most people will hand draw something in the air resemble or some other well-trained in general relativity say
I think there are some problems, Gabriela. I don't know if. Hmm. Okay, so
um,
we lost your connection. So
okay, in which part I
just 30 seconds ago. So you can start from last
okay,
concept. Sorry.
well,
Okay, so we didn't see another slide, so we just see just this. Okay, so you can start from this.
um, okay, uh, the next slide is just an example of how can we imagine what is a straight line, the notions of we are, of we have, of what is a straight line. So let us consider the following example. Imagine we are lost in a city, any beautiful city in the hills with a fantastic view or of the sea or of the city, where people were not so fond of right angles. So let us consider the case of Ciudad Universitaria, the layout of the National University in Mexico. And imagine we are asking someone for directions to go from where we are to a certain destination, say point B in the map. The answer we are given is to go straight. But not that in this case straight doesn't mean Euclidean straight, nor means the path of the shortest distance. Moreover, it is very likely that if we are the ones giving directions, they may know that there are better ways or shorter ways to get to the destination, but we simply say go straight, knowing what we mean by that. In this case, we know and understand that straight is not the same as shorter. Thus, we see that the Euclidean and indeed Riemannian geometry is kind of a degenerate geometry where the notion of a straight and shortest path coincide. What we mean by go straight is whatever you do, just don't deviate from the main road. This is the definition we will use. A straight line is a path such that a traveler doesn't deviate from it. More formally, a straight line is a curve such that is a tangent vector is parallelly propagated along itself. The question remains on who defines these straight lines. In the case of the city, it's a combination of population and urbanism. So by the time we are given directions, the paths are already there. They are given a priority. Thus, without changing the single word in Galileo's definition, we say a motion is inertia if it is straight and if it is uniform. But now we see that the straight is not as obvious as one might have imagined. So the next question is, okay, what is a force? Armed with this idea with inertial motion, we can express the physical principles as they are taught. One is the principle of inertia, when where every object maintains its inertial state of motion unless something makes it change. In this way, we can define two different concepts. One is the acceleration as a measure of the departure for inertial motion, and the other is the force as a cause of the acceleration. Whenever something is moving not inertially, we are certain that the force or no other thing is responsible. On the other hand, we have the famous Newton's second law of motion. It is essentially state the relationship between the force and acceleration. In particular, it contains a definition of force which is ontologically different from the cause of acceleration. To that end, one defines the quantity of motion or momentum or and state a kind of complementary principle of inertia, namely conservation of momentum. So in this sense, an object moving naturally conserves its momentum. A force measures the departure of such a conservation, which this definition seconds Newton's second law becomes a theorem related force and acceleration. But now acceleration can be either falling to move in a straight line or to move in a straight line but with a varying speed. But we are not told that those two notions require different geometric objects. On the one hand, we need those a priori straight lines, and in the other hand, we need to know how to measure the size of a vector. In mathematical terms, the former one requires a connection while later a metric. In the simplest case, one could simply provide the metric and use the Levi-Civita connection to define straight lines. This is indeed the case when straight lines are truly equivalent to the path of shortest distance and should suffice to venture a little further in our understanding of our basic principles. So here comes a source of confusion. In the passing from Newtonian to relativistic physics, we are not only replacing the philosophical ideas of an absolute time and space and adding the invariance of the speed of light and the equivalence principle, but we are effectively changing the foundation of which the definition of inertial motion is defined. We are resigning Euclidean geometry, providing us with or a priori and intuitive notion on straight lines to a situation in which straight lines become a consequence of a dynamical theory of geometry. The situation is slightly worse, or better if you like, since in this case, gravity not only is not a force, but it becomes the defining notion of inertia. Gravity doesn't change the natural state of motion. Gravity defines it. In this sense, gravity is non-interactions. In our exercise, we will not go as far, but we will only exhibit how we can reach the same conclusions as Newton's universal law of gravitation using a Schwarzschild spacetime in non-inertial Einstein flame. So this is, we have to be careful in defining inertial motion. We have to say in advance what the straight lines are. This is a similar exercise as the fable presented in Reichenbach's book, The Philosophy of Spacetime. It's very nice. It was published soon after the advent of the general relativity. There, he presents two parallel worlds whose inhabitants see the same universal effect, but the objective situations appears to be different. In our case, the two worlds will differ on their corresponding definition of inertial motion. In one of them, it will be that of Galileo and Euclid, while in the other, that Einstein and Schwarzschild. For Newton, gravity was a force. As we say, that means that it was something capable of changing the inertial state of motion of every massive object. But it was not like any other force in one crucial bit. If you compare the effect it has on objects on different inertial masses, the effect is exactly the same. There is no observation we can make that tell us which object is heavier. This is in sharp contrast to the electromagnetic force, where twice the charge produces twice the acceleration. So in Newtonian physics, gravity is a special kind of force. It is universal. So it affects every massive object in the exactly same manner. And there is no escape of it. As far as we can tell, it is the only force which such properties. Such law was applied to systems like a planet orbiting the sun or moons orbiting the planets, and even to obtain the local acceleration one feels when standing still on a massive body. Orbits are clearly no Euclidean straight lines. Thus, the force of gravity was responsible for dividing the planets from its otherwise Euclidean paths. This is the celebrated expression of Newton's law of universal gravitation that we are taught since middle school. But now we can consider the following situation. Suppose we are observing the solar system from above. Clearly, the paths of the planets are almost circular. Anything moving in a trajectory different from a conic section will be seem extremely odd. In fact, that was the reason the famous infamous Oumuamua object caught our attention. If something in the solar system appears to be moving in a Euclidean straight line, surely it is doing something unnatural. The natural thing to do is go around in arcs. The natural motion doesn't appear to be Euclidean. Luckily, that should not bother us at all. We have seen that the Euclidean geometry is but one among many possibilities. One such possibility was presented by Schwarzschild, a geometry where orbits around a massive object are indeed the straight lines. To a high school student, this idea may not be so clear. So let us be more specific on what do mean by a geometry. The one thing in mathematics that most people are familiar with, or at least have heard of this, is Pythagoras' theorem. Its mathematical expression is even also frequent in mathematical memes, that is c squared equals a squared plus b squared. I will assume nothing becomes much more abstract. We can change the letters for deltas. And then, assuming one has reached the final year of high school, one can imagine tiny pieces of line like this. This is still just Pythagoras' theorem, only written in a slightly fancier manner, but there are only other ways of writing it. If we inhabit a planet small enough to appreciate a walk around his surface, think as the Little Prince, for example, surely we will have reached a different version of the Pythagoras theorem. Let us call it the Little Prince theorem, which for a tiny line on an asteroid of B612 will be this, the final expression. That is the same Pythagoras theorem, just with the difference that this is in a sphere. So indeed, this is a different form from its Euclidean counterpart. The Little Prince straight lines are arcs over the asteroid and non-Euclidean lines that want to leave the surface. So our world, or at least the way we dearly perceive it, has more than two dimensions. For our world, we will consider four dimensions. In these four-dimensional words, Pythagoras' theorem could be described like this. While for Einstein and Schwarzschild can write this. In both cases, we will consider static. fixed in a single motion on a space, this particle of mass m, a distance r, from the source mass capital M. We are already know that Newton's answer is, let us see what Einstein and Schwarzschild say in this part. So a static body doesn't have a special velocity. It is not moving anywhere. But it
Gabriela,
doesn't.
you have 2 more minutes. So
Okay.
you've got to jump to the
Thank you.
conclusions.
Yeah, I'm almost ready. But it doesn't move towards the time. Thus, it does have a time velocity, but while being steady in one place is certainly the idea of inertial motion of Galileo. It is not so for Einstein, indeed. A static object in Schwarzschild spacetime experiences an acceleration. In fact, the acceleration is precisely this. This is a type of calculation that is straightforward for a physics graduate, but not so obvious for a high school. This is the message. This message is sufficiently clear. Moreover, this is exactly the right answer to the question of why the accelerometer in our phones constantly experience 1g when standing still, while the reading goes to 0 when we throw it in the air. The parabola it describes is clearly non-Euclidean, yet it experiences not acceleration. So what do we get from this? In this exercise, we avoid telling what gravity is. Instead, we encourage students to consider other possibilities. In particular, we can make use of the standard technology of our phones to exhibit a question which places the attention precisely in the ontological definition of the gravity. Is it a force? Is the parabola described by the phone an inertial motion? Gravitational physics can indeed boost the creativity of scientific thinking at an early stage, and we can take the chance to make it real. So, okay, that's all. I am Gabriela Vera. So thank you so much for listening. We will be very happy to answer your questions if we can.
Thank you, Gabriela, for your presentation. We have time for one question. No question? Just me comment on the fact that it's very important to emphasize the universality of gravitational interaction in comparison with, for instance, electrical interaction. So as you correctly pointed out, they are quite different. So we can use a geometrical approach to gravity due to it's a universality, but we cannot do that if we consider, for instance, the electrical interaction. So it's very important that when we teach in comparison, for instance, the Newton law and Coulomb law, that they have the same structure, but the effects are completely different, as you have emphasized. So it's very important from a teaching point of view to stress the difference and not only the similarities between the 2 laws.
Oh, okay. Yeah, we are trying to study the basis of all the principally the geometry. We can try to use other physics phenomena to explain as analog form.
Yeah.
So yeah, this is something that I thank you. All this observation, we will take care of that, and I don't know.
Yeah, no, of course, geometry is very important. It's the basics of our approach. So it's very important to explain by analogy in geometric formula what is the meaning of force. Okay, so we have one last speaker, Mimosa.
One question. I can't stop sharing.
I'll try to do by myself.
Okay.
Okay, Mimosa, would you try to share your screen? Okay.
Is it okay?
Yes.
Okay.
Yes, you can start.
Thank you. Thank you, Matteo, Luca, and David also. He's not here, but for having the idea to organize this kind of session, and for giving me the opportunity to have this presentation. I am from Tirana University. I am professor of astrophysics. And actually, my scientific contribution is focused on gravitational microlensing as a method for...
Mimosa, we have problem with, okay, we cannot hear you. Something happened, can you, okay.
Now?
Yeah, okay, now it's okay.
I start since the beginning of...
No, you were telling that you are a professor of astrophysics.
Okay, I am professor of astrophysics at Tirana University, and actually my scientific contribution is focused on gravitational microlensing as a method for the discovery of exoplanets, free-floating planets, primordial black holes, and other kinds of dark matter. But at the same time, I find useful and I like the popularization of scientific knowledge. And here I am using my scientific novel, as you know, named Blue Infinity, as the subject of this talk. In fact, that turns out well, as I am the last speaker of this long session, and I wish you that listening of telling somebody to tell you a story will be a good way to finish the working day, I hope. In fact, this novel, The Blue Infinity, is my second scientific novel. The first one was named Rose Point and was devoted to the exoplanet discovery. I can tell you that I won it. This novel won the National Prize for Youth Literature in my country in 2020. And in fact, I have been very proud for this prize, as much proud as for the best things that I have done in my life. So it was to tell you that it is a kind of activity that I like very much. Yes. Blue Infinity is a novel of a scientific genre. Everything revolves around Marina character, who is the daughter of an astrophysicist. Her mother, Donna, is a researcher at the Astrophysical Institute of Paris. It's a fictional, in fact. Marina has decided to devote her entire life to the search of the infinity at any place where it appears in mathematics, physics, astronomy, philosophy, art, and literature. And the reason is she made this choice is that the desire to challenge those major forces that took away her father after a grave illness. And here I underlined only two words, physics and astronomy, which are the focus of my talk today. I do not speak today about the approach of Marina to mathematics, philosophy, art, and literature. In fact, a part of Marina and Donna, as I mentioned, there are a dozen of other characters. I underlined the real, the real persons, the real scientists, or you will see writers, but they are mixed with some fictional characters. Both of them, two categories, work in real scientific centers and all love science. For example, George Cantor, mathematician, Henrietta Leavitt, astronomer, David and Gabriel, who are fictional, are astronomers. Max Born, Werner Heisenberg, and Albert Einstein, physicists. There is Mrs. Grace, a teacher at the college, students of the Princeton and Göttingen University, a student coming from Prague, and at the same time Isaac Newton, Blaise Pascal, who is a physicist and a thinker, and Giacomo Leopardi, an Italian poet. His poem named Infinity is one of the most famous of the 18th century, and he is the central character of my novel. You know, 2019 was the year of Giacomo Leopardi in Italy, and for that reason I was inspired to dedicate this novel to the infinity. And there are other characters. You see there, Professor Martin, physicist, Max, historian, Professor Paul, physicist, and Professor Russell, he is a philosopher. Edgar Allan Poe, a poet, writer, and one of the first to propose in 19th century the non-eternal universe in his essay named Eureka. All these characters, fictional or real, try to attract with their courageous pursuit to the laws of nature, including the infinity, and they follow the paths that humans started to trace since the time of antiquity. The scientific paths, philosophical paths, literary, artistic, mathematical, and physical. On the left, there is a picture shaping a question mark with 5 infinities with different colors, but I will explain a bit later this picture. And something about the organization of the novel. Each story inside the section is develops twice with 2 different views that complement each other. The first time, the story grows by means of characters as common humans. They are realistic or fragile, idealist, courageous or hesitant, but common humans. They never stop to be dreamers. And this part is named recto. Each part we have recto and verso. And after each recto, the verso develops the same line of story involving the same characters, which now prefer to maintain strong professional position. They are scientists and researchers of the infinity, and they want to communicate their hard-gaining knowledge in a simple way. The scientific themes that I developed in this novel, reflections, discussions, initially are developed in rectors, and afterwards they are treated more deeply in versos. Anyway, and even in versos, I try to keep a scientific level similar to that level of common popular science books published frequently, you know. And here are I show 2 pages. They are in Albanian, in fact, but could give you an idea about the organization of the book. So now I will try to explain some more important information in physics and relativistic astrophysics and Einsteinian physics developed in the book in the chronological order, starting from the first chapter. The first chapter happens in March 2013. There are 2 important places. One is Astrophysics Institute of Paris. I have chosen this institution as I have a long time cooperation with this group there. And Recanati, I told you, the place, the hometown of Giacomo Leopardi, Recanati in Italy. And at 21 of March 2013, there is an announcement of ESA, European Space Agency, a real one, about the then recent discoveries of the Planck satellite. Planck reveals an almost perfect universe, and it is related to cosmic microwave background. Donna, the mother of Marina, is waiting anxiously this announcement that summarizes her excellent hard work on processing large sets of satellite data. As happens always in such cases for her, she gets into imagined conversation with her hexagonal clock that comes from Syracuse. In the circular trajectory of its rows between two hexagons is hidden the infinity of the number pi. And she has also a phone discussion with her colleague, Gabrielle, who works in ESA. Sometimes later, her colleague David arrives in her office with an invitation for a party. As a group of astrophysicists, we will celebrate the discovery of a new exoplanet situated close to the galactic center. And I found a real exoplanet discovered at that period, at that moment, and studied by the astrophysicists of this institute. However, rather than moving quickly, Donna and David have a long discussion about the infinity and claustrophobia, about Aristotle, Middle Ages, Giordano Bruno, European Renaissance, Isaac Newton, Descartes, Blaise Pascal, Giacomo Leopardi, and also Max. Donna, deceased husband, a historian and a passionate researcher of the Enlightenment era. The day after, Gabriel goes to visit Recanati, the city of Giacomo Leopardi. There he has a talk with students of the college about high distances in astrophysics and especially about cosmic microwave background. The first chapter ends with the event of 70th anniversary of Marina, and David offers her a gift. It is a picture that I have shown you, but better than the picture I have shown you, with 5 infinities shaping a question mark, each one of them carrying 5 couples of opposite terms inside loops. Potential infinity, actual infinity, 1 loop. Border paradox, Zeno paradox. The man, the God. Physics, mathematics. The body and the spirit. This gift becomes the center of a lively conversation between Marina and her friends and Donna and David. So let me here to draw a list of scientific themes connected with Einsteinian physics and relativistic astrophysics I could treat during this first chapter. Cosmic microwave background, as Donna and Gabriel work with CMB data. Time measuring and atomic clocks, as Donna works close to Paris Observatory, where there is a laboratory named CIRTE, where the people work on referential systems of space and time. Gravitational lensing and microlensing, as David uses this method to discover exoplanets. Planck Observatory, Gabriel is a scientist in administration of this observatory. Big Bang model, which Gabriel discusses with the students of Recanati. Why CMB have proven Big Bang, Aristotle universe, the paradox of border, Newtonian gravitation, Einsteinian gravitation, matter, space, and time. These are a list of subjects that I discussed, and I made use of the discussion in the first part, which I named Rector, to develop more in the second part named Versa. What about the second chapter? The story is on February 2016, mostly on Princeton University and Institute for Advanced Studies, but at the same time, Donna went to her hometown. And this chapter starts with a ceremony organized for the 80th anniversary of Professor Martin, which is a character inspired by the Nobel Prize winner in physics, James Peebles. I studied his life and I liked very much the career for discovering the cosmic microwave background. And the place is in Princeton University, Peyton Hall, on 20th of February 2016. It is a conference, in fact, this ceremony devoted to gravitational waves. Only a few days before, and a real fact is paper appeared in 11 February. This paper confirmed the discovery of gravitational waves on 14th September 2015, you know. And the main speakers of the conference are Professor Martin, Nobel Prize winner in physics, Professor Paul, coming directly from LIGO Livingston Observatory, and Professor Russell, a well-known philosopher from Princeton University. I needed to have some philosophical discussion about the questions. And there are those dialogue questions and answers that develop around the concept of general relativity, Albert Einstein, merging of black holes some billion light years away, and so on. And Marina is is seated not far from Professor Martin. She came in Princeton for a semester to finish her diploma. On the other side, she notices Morgan, a young physicist, working in a project named Antares. He dives, Morgan, for discovering the cosmic neutrinos, and Marina also likes to learn diving in our terrestrial oceans to feel better the natural sensation of being inside the ocean of cosmic photons. At the same time, some 1,000 kilometers away to the east, Donna is invited to moderate a contest about the meaning of infinity organized by students of the school in her hometown. Donna does not like infinity. She considers it as an imperfection in the equation of physics. She explains that to the students as she speaks about space and time, different horizons, and Big Bang. She has also translated 3 poems to the school, to the infinity, and she shows these poems to the students. And the most known one is obviously The Infinity of Giacomo Leopardi. After finishing the conference, Professor Martin likes to walk to his office in the Advanced Study Institute. Every step taken in the known streets triggers memories. It reminds him of the work with many bright colleagues and famous discoveries. Donna calls when he arrives in his office. They have a discussion in Skype about a new project, which will focus on the better exploration of phenomena involving long distances, a network of antennas to the moon. Donna, you are so brave, thinks Professor Martin. At this juncture, he remembers another brave woman scientist, Henrietta Leavitt, who lived a century ago. And here is a list of themes, scientific themes I treated in this second chapter. You see gravitational waves, black holes, LIGO and Virgo, space-time in general relativity, TMB discovery through memories of Professor Martin, who was one of the authors of the 2 joint papers declaring the discovery of cosmic microwave background in 1964. Olber's paradox and eternal universe through Donna conversation during the contest about the infinity, and several other subjects. They are listed in the screen, and you can see that there are many things to that I could explain during this novel. And as I told before, I tried all the time to keep the same level of scientific level as the usual essays that are published frequently, recently, and during the decades. So the third chapter I could not show you here, as it is devoted to the infinitesimal, and so it is out of the subject of this talk, but I would like to finish by discussing with you why a novel. We had a session today where all our colleagues are discussing about how to render the scientific knowledge easier for our students and accessible to everybody. But why write a novel? Instead, the essays that are frequently published and welcomed, you know, and they are excellent, in fact. Both can be read and understood by a broad audience of people if written in a comprehensible manner, surely. But based on my experience, I would like to stress some advantages of the fiction. The first one, I think it lets the professional researcher become characters of a novel. The freedom of fiction allows showing their typical thinking of researchers. It permits to entangle together scientific and personal stories in such a way that any reader can find something from his own life. The second one is, I think, the fiction creates more possibilities to spread more information about real research centers, and the most important ones. We can select the most important ones. You saw here, it was Princeton University or Göttingen University. So it is the freedom of the writer to choose. And also the fiction allows presenting the philosophy of science, the way how the science develops from the known to the unknown. I have chosen a phrase of Professor James Peeble, the real one, and which is used from the fictional one, Professor Martin. He says that we operate on a postulate that nature operates by the laws that we can discover. That's only a postulate. We have no guarantee of the way the nature works, but of course we find that this postulate is very productive. And also the last one, the fiction permits to lay scientific discoveries on some intrigues, and you know, all people like, in fact, intrigues. And to finish, I would like to stress once more that the characters of the Blue Infinity are led only by the scientific truth. And thank you for your attention, and hope that you liked it.
Thank you, Mimosa. Very, very interesting presentation, mix of science, philosophy, arts, and beautiful ideas. Are there any questions? We are on time, so we have time for questions.
I have one short question.
Of course.
Yes, so thank you for the talk. Actually, the idea of putting a science discovery in story is quite, how to say, sounds like a recent trend, because when I was in Japan, I also find a lot of popular science book trying to wrap a lot of complicated physics in comics or even in novels. So I think it will be very interesting for those secondary school students or those who are fresh in physics to understand that. But I'm always wondering how effective is that, because most of the time in those stories which I have read, they spend a lot of time to, how to say, elaborate the characters, or to make some plot which is actually not so relevant to the science. So I'm thinking how to make a good balance between the two things, so that what is your idea on this balance?
Yes, as it is my second novel, I have now I have a good experience in writing. I like very much this activity, so it is the reason that I devote part of my time to writing novels. And you know, at the point of view of methodology, I decide, for example, in the case of Infinity, I decided what are the themes I need to develop. So after it is the basis of my novel, and afterwards I try to establish the fiction. So for me, the basis is the scientific themes, but this one is an important step to think about. You cannot tell everything to the people, so you have to choose what to say. And after you choose, for example, I have a section, and inside the section I decide to have 4 or 5 themes to develop. And after deciding that, I establish the story. The point of view of story afterwards, it is a very personal. We can be inspired by some friends or family or events, important events or happening in your life. So, for example, I can say you that I had my PhD studies in Paris, and since I have a long cooperation with this the centers there, so it is the second time that I use the institutions of Paris in my novels, as I feel I am inspired from these people and this city. So it is a personal position.
Thank you.
Thank you for the question.
Thank you. Yeah, that is a very interesting sharing to know about. Thank you.
Thank you. I have one question. Is it translated into Italian? Do you plan to make a translation into Italian just to read it, because we cannot read the Albanian?
I would like very much. In fact, during this Blue Infinity is published only some months ago. I have been very focused to translate the first one, and my first novel is translated in French, and okay. I think in some weeks it will be published in France. And for the second one, I would like very much that the first language to be translated be Italian, as the center is really Giacomo Leopardi. Yeah, I was really inspired by this poem, and it is in the center of my novel. So I prefer, but it's you do not have. It was my first experience in this kind of work, and it's very, very difficult to have some communication with a publishing house.
Yeah, of course.
Very difficult experience.
Okay, maybe we can discuss in the future about this. Okay, so we are perfectly on time. So this is the end of our first part of the session. The next part will start very early tomorrow at Alpha 6 Central Europe time. And there will be the talks from our colleagues from Australia. There will be the invited talk by David Blair. So if you can, I invite you all to participate. I know that it's very difficult. So in any case, I would like to thank you all for participating, and we hope to meet and to see you soon in person somewhere. And thank you for your contribution to this conference. Thank you all.
Thank you, Matteo, for organizing the session.
Thank you, Stefan. Thank you.